Yeah, thank you. So my name's Shaoshen Xue. I work as a senior research engineer at Motor Design Limited. We are a UK-based company which is a developer and a producer of the software called MotorCAD. It's a multi-physics finite element tool for the electric motor design and analysis. As a company, we also provide the consultancy services to deliver the electric motor design solutions and analysis for our client. We also participate in some of the UK government-funded research projects. So this today's topic is from a research project we've been doing for this year and the last year. It's the modeling and optimization of electric motors with hairpin windings. So here is a preview or an overview of these hairpin windings or electric motor with hairpin windings. It uses the preformed conductors to replace the random wound, the conventional one, the wires in the windings. It will provide us some benefit from using that. The first one, we can achieve very high fill factor, can be zero 0.6, 0.7, or even higher. And it allows us to do very highly automated manufacturing process by using the hairpin winding. And because of these very significant benefits or advantages of hairpin winding, this type of winding is becoming very popular in electric vehicle or hybrid electric vehicle driving applications. For example, the Chevrolet Volt second generation since 2016, the Toyota Prius since fourth generation, and recently the fifth generation from 2015, and the Chevrolet Bolt 2016. They are also all using the hairpin winding technologies for their electric motors. And talking about the hairpin winding, we can divide that into two types of windings in terms of the production process. The first one is the axial insert hairpin. So the process is like we shape the long copper wire into this hairpin shape, and we assemble that hairpins into the stator slots through this axial direction, and then for forming the wave winding, we twist each of the end of the hairpin, and then we weld that to form that wave or winding. So in this process, welding is required to connect the hairpins. So the more conductors we have, the more time consuming this process becomes. Due to the industrial experience, a rough maximum feasible solution is around 72 slots, 8 winding layers. And another type of hairpin winding is the radially insert hairpin, is also called continuous hairpin winding. It will shape the long copper wire into the wave winding, a whole wave winding, and then we can assemble this whole wave winding into the stator slot through this slot opening, so radially. So that's why it's called the radially insert hairpin. So you can see in this process, the welding and the twisting process is not required. So we can save a lot of effort and time on that. It's easier to have a higher number of slots and the winding layers. Maximally would be around the 12 winding layers we can achieve. But the disadvantage of this type of winding is that for the stator design, the open slot structure is a must, is required, because we have to insert all the windings through this slot opening here. So this will have a strong impact on our performance of the electric motors. And the advantage and the disadvantages of hairpin windings can be listed. Fill factor can be very to 0.75 or even higher to 0.8. It can achieve better thermal performance because the contact between the windings become very good. It's very close to each other. And it will enable a highly automated or manufacturing process. The disadvantages becomes it has less flexibility for winding configurations. I'll talk about this later. And it will have higher AC losses due to the bigger conductors in the slot and the higher cost due to some tooling and also additional manufacturing process. So talking about the design of the hairpin windings, we have to follow some specific hairpin winding design rules. So the first one, the number of winding layers should be even, and the wires that belong to the same path must be covering all the layer of the slot. That is to ensure the same inductance for each parallel path. And the wires that belong to the same path must cover all the slot per pole of that phase. That is to ensure the same back EMF for each parallel path. So both of these second and the third rule of the hairpin aim to ensure that there is no circulating current between the parallel path. So for example, for this one, when we have a parallel path number equal to 1, that we basically do the transpositions for the hairpins and cover all the slots, all these layers of the hairpins with the hairpins. And when we have a parallel path, 2 parallel paths, for example, for the red and green color, we basically do the transposition between these slots, go up and down to cover all the all the winding layers here. So similarly for the green color, so the parallel path 2, we do the same to cover all the winding layers. And also for these slots per pole of one phase, we also cover all these 2 slots per phase per pole to ensure there's no circulating current between the parallel path 1 and 2. So that is for these 2 rules, we can transfer that to some specific equations. The first one is the number of conductors per parallel path divided by number of layers must be integer, and the number of conductors per parallel path divided by number of slot per pole per phase must be integer as well. So as long as we can meet all these 2 requirements, that is to say we have a feasible hairpin winding configuration. So for example, for this one, when we have 36 slots, 6 poles, and number of parallel paths equal to 2, and when we have 8 number of hairpin winding layers, we can see that these 2 numbers are all integer. So this is a feasible design. On the other hand, for this design, when we change the number of parallel paths from 2 to 8, so this number becomes 1.5, which is not integer, it's a fractional number. So this is not a feasible design anymore. So in MotorCAD, we integrate these design rules in our software. When you input all these winding configuration parameters, the software will tell you which is this design a feasible design or not. So which is quite convenient for our users. So here comes the case study to design and modeling of electric motor with the hairpin winding by using MotorCAD. And we'll do an analysis on the DC and the AC copper losses. And we also going to optimize the number of winding layers and the conductor size to maximize the motor efficiency. So here is the motor example. It has 36 number of slots, 6 poles. We have a number of serial turns per phase, which is 12, V-shape IPM, and all these parameters and materials are listed here. So here is the model, the topology of this electric motor. And we can model that winding configuration in MotorCAD. This is what it looks like when we model that. And after modeling this electric motor here, here we comes across a problem. So how to optimize the electrical machine to achieve higher efficiency by using the hairpin winding? Basically, we can optimize the number of winding layers. So when we can use 2 layers of winding, or 4 layers, 6 layers, or 8 layers. So when we increase the number of layers we're using, we can reduce the AC losses normally for the electric motors. But as you can see here, when we introduce more number of layers of winding, the more insulation layers we also can find here. So that means the fill factor will reduce significantly as well. And the resistance of the electric motor will increase. That means the DC loss will increase as well. So this will become a trade-off between AC and the DC loss when we change the number of layers we're using for the hairpin windings. So yeah, this is overview or results of the fill factor when we use different number of layers. So in these 4 designs, we use 2, 4, 6, and 8 layers of hairpin windings. And we also change the parallel path from 1 to 4 to keep the number of serial turns per phase constant. And we can see that the slot fill factor will decrease from 0.77 to 0.65 when we change the winding layers from 2 to 8. So this is a very significant decrease of the slot fill factor. So here shows some results at different operating points at 1,000 RPM, which is a relatively low speed, and 12,000 RPM, which is a relatively higher speed. We can see different behavior of the losses. So for example, at low speed, we can see that with the increase of the winding layers, the DC loss increase significantly, while the AC loss increase significantly, while the AC loss decrease slightly. But as the DC loss is dominating at low speed, the total loss will even increase with increase of winding layers. That is to say, there is no benefit to use a higher number of winding layers, as the overall total copper loss will increase with the winding layers, and the cost we use higher number of winding layers also increases. There's no benefit at all. But when the electric motor speed getting high, the benefit we can see here is the AC losses decrease significantly with the winding layers. And at this operating point, the AC loss dominating, so the total loss will also decrease significantly with the winding layers. So here are some conclusions. When the speed is low, the copper loss increase with the number of the winding layers. When the speed is high, the copper loss will decrease with the number of winding layers. So how to achieve the better performance for the electrical machine by minimizing the losses and maximizing the efficiency by using with the hairpin winding. So we have to do a comprehensive analysis considering operating points, and ideally we have to do a driving cycle analysis, which is highly recommended by us. So here is the results for the different driving cycles for the 4 electrical machines with different number of hairpin layers. We can see that for the WLTP3 driving cycle and the NEDC driving cycle, both of these driving cycle, we can see the similar trend when we change the winding layers. The electrical motor will get less copper loss when we change the winding layers from 2 to 6. And then if we increase these winding layers even higher from 6 to 8, it will increase, the loss will even increase a little bit. And this figure shows the efficiency of the electric motors under different driving cycles. So we can see that the optimal number of winding layers is 6 for this electric motor. So there's a conclusion that the higher number of winding layers not always lead to better performance or better efficiency for the electric motor. The optimal number of winding layers must be identified by the analysis considering different operating points and different duty cycles. And another issue we can consider is the conductor size. So we can optimize the conductor size to achieve better performance for the electric motors. So here is some background of this method. So normally when we design an electric machine, we would like to fill the slot by the conductors as much as possible. But for hairpin windings, the AC loss becomes an issue. And for example, if we like this, we have 6 layers of hairpin windings. If we fill these slots pretty much, and we can see that the flux density at the very close to this slot opening becomes very high. So this flux density here and the changing and kind of a changing magnetic field here will cause significant AC losses on the conductor. So if we reduce that conductor size a little bit to avoid the slot opening here, we can see that the flux density becomes much lower. That means the AC loss will reduce significantly. But on the other hand, the DC loss will increase significantly. So this is another trade-off between the DC and the AC losses when we design this hairpin winding. And in this design, we can use the conductor width ratio instead of the actual width. So it's defined as the actual width divided by the reference width of this hairpin. And similarly, for the conductor height, the ratio becomes the actual height divided by the reference height. So when the ratio is 1, that means we fill the slots as much as possible. Pretty much all the slots are filled by the conductor. And for example, when this ratio is 0.5, so that means 50% of these slots are filled by the hairpin winding. So here comes some results. So similarly, with the analysis with different winding layers, we have 2 operating points to do some example here. So the 1000 RPM, low speed, and high speed 12,000 RPM. So at low speed, we can see that the reduction of conductor width ratio will lead to an increase of the total loss here, since we'll introduce a lot more DC losses here. And at high speed operating point, we can see there's a kind of optimal conductor width ratio happens at around 0.5, and then it will decrease again with the decrease of the conductor width ratio. And for the conductor height, we'll find a similar trend for the DC and AC losses at low speed, and at high speed, you can see this trend optimal number happens at around 0.85. So here is a conclusion that is not necessarily always good to use the higher or bigger conductor size for the hairpin winding. We have to find out the optimal conductor size to get the maximum, to maximize the efficiency for the electric motor. So with the optimization on the conductor size, we can find that here is the comparison between the original and the optimal designs. So for the original designs, the conductor width and the height are designed to fill the slots as much as possible. And for the optimal design, we actually found the optimal size, which are all smaller, which is smaller than the original conductor. But with this design, we can see the total copper loss even reduced significantly, all at around 10%. And the overall efficiency we can achieve is much higher than the original one. At the meantime, we can see the total copper weight we are using is also 10% less than the original one. So this means we can achieve better performance by using less copper for the hairpin winding. So this is the benefit. This is why we have to optimize this electric motor or the hairpin winding for the electrical motor to achieve better performance. So here is the conclusions by this study. The first one, using a higher number of winding layers does not always result in lower copper loss, and using bigger conductors to achieve higher fill factor for hairpin windings does not necessarily lead to higher efficiency. So the number of winding layers and the conductor size should be optimized considering driving cycles and operating points when we design the electrical motor. So yeah, that's it. Thank you.